Welcome to the fourth episode of the Coordinate podcast. I'm your host, Soubhik. AI is making intelligence digital. Crypto is making institutions digital. Digital intelligence needs digital institution. The mission of this show is simple. Talk to the most fascinating entrepreneurs and intellectuals defining this digital future and extract lessons that you can actually apply. Today, we are going deep dive into the future of Ethereum's infrastructure. Here are my questions at a broad stroke. What is Lean Ethereum? And what prompted this immense work stream? How will the consensus layer of Ethereum evolve? What would the execution of layer of Ethereum look like? How is Ethereum preparing for the post-quantum future? To explore all that, we have the man himself who kickstarted all this work, Justin Drake. Justin, welcome to the show.
Hi, Soubhik. Thanks for having me. Great to be here.
Justin, I still remember that fateful day back in DAppCon 2024, more than a year back, when you announced the Lean Ethereum concept. I think it was called Beamchain at that time. It received quite a polarizing response at that time. Some people praised it for this being a forward-looking. Some people criticized it being not enough with the timeline described. So I want to start with what were the shortcomings in today's Ethereum infrastructure that prompted a rethinking of the whole Ethereum's infrastructure.
Yeah, I think the major thing that Beamchain and now Lean Consensus was trying to address was a change of mindset. And as you put it, it's trying to be forward-looking and start from the end game, if you will. The way that Ethereum governance currently works is that we start with the status quo, and then we make baby steps forward. We make these incremental changes. And a lot of the time, we adopt a lot of the technical debt that we've accumulated, and we're not focused on cleaning that up. And so we're kind of making these baby steps forward, and that has all sorts of second-order consequences. One of them is that we're not as ambitious, right? Like part of the design space is not opened up to the same extent relative to if we were to start from a clean slate. So really, as a researcher, I felt that we had a lot of big ideas in the Ethereum roadmap that would be difficult to implement in an incremental fashion. I felt that we could clear off most of the roadmap items, but there would be one or two or maybe three that would be very difficult to do incrementally. And I thought, why don't, for those like really difficult roadmap items, start from scratch, clean slate, and in doing so, have an opportunity as well to clean up the technical debt.
So can you go a little bit into details? Exactly what are the pain points in today's infrastructure exactly that motivates this rethinking? What are the technical debts that are there from the previous years of development that has been done?
Right. So the two big ticket roadmap items that I felt were difficult to do incrementally were, number one, post-quantum security, because it basically involves ripping out the cryptographic guts of Ethereum as it exists. And the cryptographic guts touch most of the code base. And so in and of itself, moving to post-quantum is kind of a rewrite. And the second big ticket item is known as fast finality, where instead of finalizing on multiple epochs, roughly 15 minutes, we would finalize in a couple of slots. And again, that's kind of such a major re-architecture that I felt that it was mostly a rewrite. And if we're going to do like two big rewrites, we might as well bundle them together for efficiency reasons. And in terms of like some of the technical debt, one of the things that we want to get to long term is to be able to snarkify the entirety of the consensus layer in real time using commodity hardware like a laptop CPU. And this can only really be done if no parts of the design are snark unfriendly. And so in some sense, by starting from scratch, we can make sure that we don't make all of the mistakes that are now obvious in hindsight, but were very much non-obvious 5-6 years ago. Another kind of reason to start thinking more from scratch, from first principles, is that the beacon chain, when I gave my DevCon talk, was roughly 5 years old. And I was planning 5 years into the future when the beacon chain would be 10 years old. And so, 10 years is a long amount of time. We will have learned a lot. And I felt that there was an opportunity to have proof of stake 2.0, if you will, because, Ethereum was one of the first chains to introduce a proof of stake. And, in hindsight, we have made a lot of mistakes.
Since these were the problems, it will be worth going at a high level. How does Lean Ethereum try to solve each other?
Right. So in my DevCon talk, I really only talked about lean consensus. And the reason why we changed the name from Beamchain to lean consensus was about because of a trademark collision on the word beam. But that was actually for the better, because in renaming the project, we made it more ambitious. So instead of just looking at the consensus layer, we started looking at all of the layers of Ethereum L1, including the execution layer and the data layer. And just like we need to be ambitious at the consensus layer, I felt that we also needed to be ambitious at the execution layer. And the most ambitious project here was the ZK EVM project, which would allow us to dramatically increase the gas limit without hurting the decentralization of Ethereum L1. And many people back then felt that it was, a pipe dream, that it was like sci-fi. How could you have these very cryptographically expensive tools known as ZK VMs prove the entirety of Ethereum in real time? And in real time, we mean within one Ethereum slot, so that the proof for a block arrives before the next block. And so a lot of 2025 was convincing the world that real-time proving is indeed possible with reasonable hardware. And the performance improvements have been so great that now, in 2026, we take it as granted that, yes, obviously, we're going to do real-time proving of Ethereum L1, and we're going to dramatically increase the gas limit. And the numbers that we have in mind nowadays is 1 gigagas per second for the L1. So if an average transaction consumes 100,000 gas, that's 10,000 TPS.
You mentioned that you started with lean consensus. That was the original concept before it expanded to a lot more stuff. So what does lean consensus comprises of? Is it just fast finality? There is a censorship resistance. Is there peer-to-peer, like at the networking stack? What are all the fine-grained details?
Yeah, so what I did in my talk at DevCon is that I showed the entirety of the roadmap as I saw it, and there were like 9 different items that needed upgrading. And I felt that most of these items could actually be done incrementally over the next few years. And that includes things like censorship resistance, like Fossil. It includes things like EPBS, which we're shipping in Amsterdam in the next fork. But the items that were very difficult to do incrementally were post-quantum and fast finality. And really, those were the two that I was focusing on. There were a couple more. So the first one I already mentioned is this idea of snarkifying the consensus layer in real time. That requires a snark-friendly consensus layer to be built up. And then there was a fourth item, which was shorter slots. Specifically, I had 4-second slots as one of the goals. And I feel like maybe I was a little bit wrong on shorter slots in thinking that it couldn't be done incrementally, because now there's a lot of desire and a lot of effort to reduce the slot duration. And I am expecting maybe in H star or in I star some sort of slot duration, but it won't be the end game. It might be 8 seconds or 6 seconds. And what I'm hoping we can do with a from scratch rewrite is just completely rethink the slot structure and push it to its limits. And I have this meme which I call SOL slots, SOL, where SOL stands for speed of light. So ideally, we just need to look at how many ping times do we need to account for in a specific slot, and then have a number that we're comfortable with for the ping time, one that is friendly to decentralization, and then denominate our slot duration in some multiple of ping times. And that will, in some sense, be the end game slot duration that we can't squeeze anymore without sacrificing decentralization.
So on this slot duration, so this is all part of faster finality. So it has two parts. One is the number of slots to finalize, and then within slots, what is the per duration, right? So exactly. I see that there has been work on something called 3-round SSF. Can you explain what is 3-round SSF?
Yeah, so 3SF stands for 3-slot finality. And the idea is that the latency that it takes to finalize is 3 slots. So there's 3 rounds of attestations. And actually, right now, we're moving to even more modern finality designs, which sometimes have 2 slots to reach finality, and sometimes even just 1 single slot. So we have a whole team within the Ethereum Foundation protocol cluster called the consensus team, and they're looking at this, and they're cooking something which they're calling endgame finality. So it's very much appropriate for the Lean consensus efforts. And I expect it to have, let's say, 2 slots of latency, but maybe have a fast path in the optimistic case, which only has.
So this is the same style as like how Minimate or other like new protocols have come up, which is like 2 rounds, but you need more resilience, like 5F+1, something like that. So that kind of theme is there.
Yes, exactly. So there's a lot of inspiration from Minimate. And actually, one of the things that the consensus team is trying to do is to take Minimate and add this notion of economic finality, meaning if you have an individual consensus participant being dishonest, having the corresponding slashing conditions. And the other thing that they're trying to do is to add what's called dynamic availability, meaning even if a large portion of the validators go offline, you still have chain progression. So you still have new blocks that are being created, even though the finality itself has stalled.
I see. Okay, so coming back to the second part of the question on FastFi, you need per slot to be also smaller and smaller. So right now it is 12 seconds. I believe you guys are targeting lower, like 4 seconds, even lower. What is an anatomy of a slot? Like, what are the most critical paths in a slot you have to keep in mind while designing, like putting an estimate on what should be a per slot time should be?
Yeah, so there's all sorts of things going on within a slot, and you can call them sub-slots, if you will. One thing that needs to be done is that the payloads, for example, the L1 block needs to be gossiped to all of the attesters. And then once the attesters have received the block, they actually need to gossip their attestations. And in the case of Ethereum, because we have so many attesters, we need to aggregate the attestations in order for them to be efficiently verifiable. And then that's yet another subslot dedicated to the aggregation of these attestations. And we're actually playing a lot with the slot structure with some of the upgrades that are coming. So, for example, we have EPBS that adds more complexity to the slots, where basically we have 2 phases where phase 1, the proposer will pick a block header, and then in phase 2, the corresponding builder will reveal the payload. And sandwiched between these two, you have what we call the PTC, the Payload Timeliness Committee, which basically is a small committee of validators that will vote as to whether or not the proposer kind of picked the header in time. And then you have even more complexity that's added with Fossil, where you have these includers that are going to gossip these so-called inclusion lists. And then similarly, you have these committees that are observing the timeliness of the various actions. And I think we're going to learn a lot from the incremental upgrades around how to best think about these subslots and play around with them. And so today, I'm actually fairly relaxed and laid back about the subslots specifically. It's somebody else's problem. We're just going to learn through the passage of time, and then when we deploy Lean consensus, we can just pick and choose all of the best practices. One of the things that people are definitely not working on right now in an incremental context is the post-quantum cryptography. Right, for a very long time, post-quantum cryptography was considered to be a far distant thing. It was important, but not urgent. And the Oracle devs process only works on urgent things. And so that means that some of the important things that are not urgent are not being worked on. And so this is where a lot of the value add, I guess, from my perspective, is. So we have now a whole team of people that are specifically working on this less urgent but still important post-quantum security.
One thing, while you were explaining the slot anatomy, you mentioned about this this attestation, which is like basically which requires propagation of blobs and the block. And EF is working on the Teragas, and then there's a new version of Gossip Sub. That at the networking stack, what are the critical like improvements that you guys are working on that helps in minimizing the slot window? And what is like, in fact, maybe going over in details, what is Teragas, what is Gossip Sub's next version of Gossip Sub looks like, and how does it integrate with the rest of the architecture?
Yeah, so when we introduced the beacon chain, we used this library called libp2p, which was developed by the Falcon folks. And one of the libraries is called a Gossip Sub, which is basically a mechanism to distribute information in a peer-to-peer way. Now, kind of 6 years later, if you will, we've learned a bunch of lessons, and we now have internally to the EF a dedicated team, the networking team that is led by Raul, and they're working on something called ETH-P2P. So this is something that should be open sourced within a few days, possibly next week. And the idea of ETH-P2P is to design a protocol which is much more minimal than libp2p, much more tailored to Ethereum's use case, and much more efficient. So one of the big improvements is this idea of erasure coding large messages when they're being gossiped. So if you have a large message, you kind of erasure code it, meaning that you add a batch of redundancy, and then you chunk it into these small chunks, and you're going to send to your peers different small chunks. And when sufficiently many chunks have been disseminated, that's enough information for you to reconstruct everything. And the upshot here is that you have significantly more efficiency in terms of bandwidth consumption. So instead of having to send the whole block to all of your peers, you just send them these smaller chunks, and you send different chunks to different peers, and that allows ultimately for this reconstruction process. And this is technology that Solana has put in place and is very proud of, in the context of Turbine. And really, it's a low-hanging optimization that we ought to have in Ethereum very soon. And there's 2 versions that have been implemented. If you're curious, there's one based on Reed-Solomon erasure coding, which is just the simplest polynomial-based encoding that you could think of. And then there's another version called RLNC, which is a more fancy erasure coding. But unfortunately, this more fancy version has a lot of patents associated with it. So it's probably not going to be one that we can use in Ethereum. But the good news is that the simple Reed-Solomon version is almost as efficient as RLNC, and so we won't be losing much from a performance standpoint. Now, you mentioned PDAS and the blobs. This is something that could benefit from this move to ETH P2P and the erasure coding, especially as we start cranking up the number of blobs and the total bandwidth consumption of validators increases.
If you guys have already benchmarked some numbers that you are projecting to have, is so when this comes live, what kind of throughput will the Ethereum as an infrastructure will have?
Yeah, so ETH P2P is like, and all of the short-term networking stuff is incremental improvements that I'm not actually focused on. This is not part of the end game, if you will. If you project yourself to the end game, my personal goal is to get to the Teragas frontier for the L2s. What does that mean? It means that all L2s combined have enough data availability to support 1 teragas per second. Now, again, if you have an average consumption of 100,000 gas per transaction, that amounts to 10 million transactions per second. And if you want to look at it in bytes, it's 1 gigabyte per second, which is orders of magnitude more than what we have right now. And there's a couple things that I guess will help us get there. One, all of the learnings that we'll have in the short term from the incremental improvements, that's going to be very important. 2, we're going to have a Nielsen's law, which basically is the equivalent of Moore's law for bandwidth, which says that every year bandwidth of a commodity internet connection will grow roughly 50%. And when you compound 50% over 10 years, you get roughly 100x. And then the third thing that we're looking at is basically a from scratch redesign of the blobs that would be bundled with the move to post-quantum. So the blobs as they exist today makes use of this cryptography called KZG, which is not post-quantum secure. So we know for sure we have to make a migration. And we're looking at designs, for example, inspired by Celestia. So there's something called ZODA, zero overhead data availability. Now, unfortunately, Celestia makes various assumptions that don't translate well into the Ethereum context. So they assume, for example, an honest majority for data availability. This is not an assumption that we want to make. So we're going to have to work quite a bit harder than Celestia in order to achieve that. And one of the candidate ideas, which seems very promising, is to reuse the cryptography that we're developing for the aggregation of post-quantum signatures for the data layer as well. So we have this infrastructure called Lean VM, which is a minimal ZK VM, which is especially optimized for hash-based cryptography. And the idea could be that we could basically prove the correctness of the Merkleization of an erasure code of a blob. So that's a bit of a mouthful, but basically you have a blob, which is a piece of data. The way that it works is that you erasure code it, and then you have some sort of commitment to this. And the hard technical thing is to make sure that your commitment is reasonable. It matches a valid erasure coding of the original data, and like the brute force way of doing it is just to snarkify the whole Merkle tree and the encoding. And this seems to be something that we could potentially do with an extremely well optimized Lean VM.
So in there are actually two parts. One is you do the encoding, and then you have to prove that the Merkle root, it is tied with that Merkle. So there are two parts of the proof here.
Exactly.
Okay. So switching gears, talking about censorship resistance. So Ethereum is working on fossil. Can you explain what is today's state understanding of what fossil looks like? Because it has, over the years, like last 2-3 years, there's been a lot of improvements on inclusion list concept. It started with that, and now we have fossil. What is fossil right now? And if there are any loopholes that you guys see that you are working on for future iterative development?
Yes. So fossil right now basically proposes that at every single slot, we would have 16 randomly chosen validators that would each have the option to propose what's called an inclusion list. Now, what is an inclusion list? It's the same thing as a block in the sense that it's a set of transactions, but they're unordered as opposed to being ordered. And the rule is that the block builder who will build the final ordered set of transactions need to include the transactions from the inclusion list so long as there's actually enough space to include them. And with EIP 1559, the blocks are on average half full. And so, there's usually a lot of space unless there's a spike of demand for all of these transactions in the inclusion lists. Now, one of the improvements that we're looking to do beyond this simple design is to actually open up the space of who can be an includer, meaning who can submit these inclusion lists. So instead of limiting it to just the validators, for which you need 32 ETH minimum, you can open it up to anyone who has at least 1 ETH, for example. And they don't have to be validators. They could just be ETH holders in an EOA. And the idea here is that if you have, for example, 1 ETH in an EOA, you can sign a message to register your interest as an includer, and you would be part of this random sampling of includers every single slot.
So this function, right? I want to register, say, as an includer, so it will be part of the get functionality itself. At that level, you guys are adding a function here.
Yeah. So
is it like a native opcode or something like that?
Yeah. So traditionally, the researchers have been thinking about fossil as being a consensus layer thing. And the reason being that it's the validators who propose the inclusion list. But like recently, we had this workshop in Cambridge, and the conclusion was that actually maybe it's much more natural to think of fossil as being an execution layer thing. And there's several reasons here. Like one is that we're talking about transactions at the execution layer that are going to be forced in execution layer blocks. And two, we should be allowing anyone who holds ETH, not just the validators, to be able to make these inclusion lists. Now, how exactly you register your interest, that hasn't been fully defined. I guess one hacky way of doing it would be to have the equivalent of the deposit contract, but for fossil. So you could have like a smart contract where you just make a transaction registering your interest. But yeah, the cleaner way would be, as you said, to have some sort of an opcode which would say, hey, I want to be part of the fossil list.
Ethereum had also this proposer builder separation. There has been a lot of variation on this, like maybe few variations on that. And is there going to, and I was while I was going through the Lean Ethereum docs and details, I've noticed that there's something called attester proposer separation, also APS. So what is EPVS today? What is APS? Why we need another thing?
Yeah, absolutely. I mean, one thing I'll note as well is that a lot of these things, like fossil, like EPBS, even APS, these are things that could be done incrementally. They're not too invasive in terms of changing the code base, and maybe best not bundled with the Lean consensus fork. But to answer your question, EPBS or PBS today, proposer builder separation, as the name suggests, is that it says that when a new block is formed, there's actually two actors that are involved. There's an unsophisticated actor, which is the proposer, assumed to be a validator. And there is the builder that is sophisticated and does the heavy lifting in terms of making sure that the block is the most economically valuable. And the reason that you need this cooperation between the two entities is that the proposer is the one that has the right to sign off on the inclusion of a block in the blockchain, but they don't have the computational power to actually build these economically valuable blocks. And today, we have something known as MEV Boost, which is an off-protocol way to have this market of builders get connected to the proposers, and it's done via centralized entities known as relays. And that leads to quite a complicated pipeline where we have the builder, the relay, the proposer. What enshrined PBS does is that it attempts to remove the relay from the equation. So as there's now an enshrined notion of a builder, so the builders can register on chain, saying, "Hey, I'm now kind of an official builder," and they're collateralized, and now they make bids directly to the proposer that are collateralized by the ETH that they used when registering. And as I mentioned previously, there's this two-step process where step one, the proposer will commit to a block header. Presumably, this would be the block header with the largest bid, and then there's this payload timeliness committee that ensures timeliness of the payload, and then you have the reveal of the block corresponding to the builder. Now, what APS is trying to do is to simplify the pipeline even further. So instead of having both the builder and the proposer, you just have the builder. And the way that it works is that you auction off the slots in a market which is orthogonal to the validator market. So instead of randomly sampling from the active validator set, you're going to randomly sample from the builders that have registered their interest as builders. One of the nice things here is that it cleanly decouples MEV from being a validator. So today, if you're a validator, you receive MEV, and that has several negative consequences. One is that it incentivizes you to play so-called timing games. So you have to be very sophisticated at the networking level. It incentivizes collocation to the relay, and that's bad for decentralization. But there's another reason why it's bad for decentralization, which is that when you do win the proposer lottery and you get selected, you get the MEV corresponding to that block, and that's extremely spiky for two reasons. Reason number one is that you only get selected as a proposer extremely rarely. about once every 6 months. So that in of itself is a lottery. But even once you have won a specific slot, the amount of MEV per in that slot is also going to be highly variable. It could be 0.01 ETH, or it could be 100 ETH. And so what that means in practice is that the average amount of MEV is significantly higher than the median amount of MEV. So if you take a typical validator on Ethereum, they're making less money than the average validator. And so that incentivizes pooling, which is infrastructure that adds complexity and to an extent is also centralizing.
I see. So you mentioned, I think multiple times, this timeliness committee. Is it like whenever proposer proposes its block, this timeliness committee checks that whether the proposer has sent its proposal within a certain window? Is that what this timeliness committee's job is?
There's two aspects of timeliness. There's timeliness of the selection of the header, and there's also timeliness of the reveal of the payload. And payload timeliness committee basically suggests that actually this committee is for the payload, not the header. So as a correction there relative to what I previously said. But yeah, it basically is due to the fact that we have this additional step that we don't have right now, which is the broadcasting of the payload separate to the header, and so we need this additional committee. But again, like these are upgrades that are extremely incremental and are happening like literally in the next fork in Amsterdam. Like a lot of my focus nowadays is not at all on the incremental stuff. It's on the end game Lean Ethereum, if you will, which to a very large extent is the post-quantum cryptography.
Touching on the post-quantum part, so you have this lean execution, the ZKVM, which you guys are working on. What exactly is it? Like, is it a new execution layer engine that all validators are going? Like, what is the change from today's thing to this new ZK EVM world?
Yeah. So what we're working on primarily in terms of post-quantum cryptography right now is actually at the consensus layer, not the execution layer. Right now at the consensus layer, we have something called BLS signatures. And they have this amazing property of aggregation, meaning that if you have multiple such signatures, you can add them together and only verify the aggregate as opposed to verifying them individually. And the need for aggregation is even more pronounced in a post-quantum context. And the reason is that the individual post-quantum signatures are at least 10 times larger than the BLS signatures. So rough order of magnitude, BLS signatures are 100 bytes, and the post-quantum signatures are at least 1 kilobyte. And so the specific technology that we put in place is to do the aggregation using a SNARK. So we have these hash-based signatures that the attesters would be producing at every slot, and we use a hash-based SNARK to compress all of these signatures in a single final proof. And where I guess things get a little confusing is that the aggregation is done using a ZKVM without the E. So it's not a ZK EVM, it's a ZKVM. And we've called it Lean VM. Why Lean VM? Because it's an extremely minimal and lean ZKVM. So specifically, the ZKVM that we have only has 5 instructions. It has add, multiply, it has a jump instruction, a memory instruction, and a hash precompile for Poseidon 2. So that would be the hash function that we built everything on top of. And this minimal ZKVM could potentially also be used, as I mentioned, at the data layer to prove the correctness of the Merkle root that we were talking about. Now, at the execution layer, where we have the EVM, we have a completely different situation. And here we're indeed building ZK EVMs. And the way this is being approached right now is to actually tap into the industry of various ZKVM vendors. So we have, for example, Succinct, which is famous for its ZKVM called SP1. We have RISC0 and ZISC and Pico. And what we're seeing is that a lot of the ZKVMs are what are known as RISC-V ZKVM. So the ISA that they have picked is RISC-V. And one of the very nice things about RISC-V is that you can take various high-level languages, like Rust, like C, C++, Zig, and you can compile them to RISC-V. And so what that means is that if you have complex programs like an EVM implementation, you don't have to be a Snark expert in order to Snarkify them. Now, the major risk with these complicated ZKVMs is that they have bugs. And so the strategy that we've taken is to lean quite heavily on diversity. So instead of having just one ZKVM, we actually have 5 of them. And the idea is that if 3 of those 5 agree, then that's the source of truth. And that gives us good safety, meaning that if you want to have an invalid proof, you would have to compromise 3 of the ZKVMs. And it also gives us good liveness, meaning that if it's impossible to produce a proof for 2 of the ZKVMs, you're still good because you can lean on the other 3. And what we're trying to do is to minimize the so-called correlated failures between the ZKVMs. So we're trying to make sure that they're built on different stacks from different teams, and we're trying to have different high-level implementations of the EVM that will be compiled to different ZKVMs. And so the strategy to lean on diversity is very similar to what we have today with the diversity of consensus layer clients and execution layer clients.
So going back to the ZK VM, which is for the snarkification of the consensus layer, you mentioned that you guys have chosen the Poseidon hash, which is one of the post-quantum. I believe there are many post-quantum. So was there a consideration why Poseidon hash might be the most appropriate one for the Lean Ethereum effort?
Yeah, so in general, if you take any hash function, or at least most hash functions, they're believed to be post-quantum secure. So if you take SHA-2 or Blake or Ketchak or Poseidon, they're all believed to be post-quantum secure. But the important thing is when you're building your signatures and your snarks is to only use the hash function, and you're not introducing other assumptions like the discrete log, which is not post-quantum secure. Now, why Poseidon? It's not because it's post-quantum secure, but it's more because it is snark friendly. So the way that traditional hash functions are built is that they will they will use like binary gates like XORs and ANDs and shifts. And these binary operations are not at all friendly to snarks. And so instead, we have these so-called arithmetic hash functions that are built using finite fields and matrices and polynomials. So, for example, you're raising elements to the power 3, and then you have these vectors that you multiply by matrices, and this much more arithmetic way of scrambling things internally leads to at least an order of magnitude performance. So the delta between Poseidon and SHA-2 is at least 10x when it comes to snarkification. And because we want to be able to aggregate as many signatures as possible per second, it's it becomes very important to pick a good hash function. Now, the main downside of picking Poseidon is that it's a new hash function. And by new, I mean that it's only 6 years old. And traditionally, when you're working with a hash function, there's this baking time where it takes a long time for the community to get comfortable with this hash function. And unfortunately, the way that most hash functions are designed is that their security comes from the lack of known attacks, as opposed to the existence of a security proof of that specific hash function. So the best that we can do basically is encourage as many people around the world to try and attack it. And if all of these people simultaneously fail, then after some period of time we can declare it to be safe. That's how hash functions are designed. And roughly speaking, the baking time for hash function that I have in mind is 8 years. Why 8 years? Because when Satoshi picked SHA-256, it was 8 years old, and when Vitalik picked Ketchak for Ethereum, it was also 8 years old. So hopefully, in 2 years' time, roughly speaking, we'll have this hash function which is 8 years old and fairly well battle tested. And the good news is that the Ethereum Foundation has really tried to accelerate the analysis of Poseidon 2. So we're organizing a lot of workshops. Last year, we organized 3 different cryptanalysis workshops. We're organizing 2 more this year. We've given a lot of grants to academics, and we also have bounties. So if you can break kind of toy versions of Poseidon, we'll give you money. And there's a website, poseidon-initiative.info, where you can learn more about this. And very, very recently, we decided to up our game and to announce a $1 million bounty for breaking Poseidon. So we're going to have a new website called poseidonprize.org, and we're going to have the rules basically be described very, very soon. And if you're interested in learning more, on March 20th, we're going to have an ETH-proof call dedicated to the security of Poseidon. And if you DM me, I can add you to the calendar invite.
So listeners, please listen to Justin and log in into that website and to that call. So I want to also go back to this aggregation part. So correct me if I'm wrong or if I'm right in this, that so this aggregation, for each slot, the next slot proposer is aggregating the signature. Is that correct?
So
and they are running this ZK VM for snarkifying the signature aggregation. Is that the understanding?
Yeah. So unfortunately, the proposers are assumed to be running on very weak devices, and they don't have the computational power to aggregate all of the signatures. Right. We're talking about a very, very large amount of signatures. So if you look at Ethereum today, we have 32,000 validators that are attesting at every given slot. So that's 32,000 signatures in 12 seconds. So that's a throughput of thousands of signatures per second. And the way that we deal with this immense throughput is by splitting the load over multiple subnets. So we have something like 16 different subnets where we're splitting the load. And within each subnet, we have multiple aggregators that have been nominated to aggregate. And the reason why we have multiple of them is to hedge against censorship of a minority of attesters. So if we have multiple of them, then we're in a good shape. Now, what we're suggesting to do with a lean consensus is to allow anyone to be an aggregator, to opt in as an aggregator, as opposed to having dedicated aggregators. And this basically allows for the default validator to come in with extremely weak validator like hardware requirements. The meme is that even if you're on a Raspberry Pi or weaker, you should be able to participate as a validator. And so instead, the assumption that we're making is that only 10% of the validators have sufficient hardware, namely a laptop CPU, and they would basically opt in to becoming aggregators in these subnets. And then we will have multiple layers of aggregation where the aggregates within the subnets would be communicated to a next round where you would have aggregation across the aggregate. So you have meta aggregation, if you will. And then there's a final aggregate, which is picked by the next proposer. But this is a very cheap process of just picking the best aggregate, as opposed to the next proposer having to do the aggregation themselves.
Going to the post-quantum future, I noticed that in many documents around Lean Ethereum, something called XMSS. What is it? How does it relate to the rest of the things that we talked about?
Yeah, that's a fantastic question. So the probably the most important letter in XMSS is the M, which stands for Merkle. And actually, interestingly, Merkle came up with these signatures called Merkle signatures back in 1979, so almost 50 years ago. And that was the very first time that the notion of a Merkle tree was introduced. So for a very long time, the blockchain industry has been making use of the Merkle tree part, but not the signature. And now we're kind of going back to the origins and actually using Merkle trees in the original intended use case. So what is XMSS? What are Merkle signatures? Basically, you start with this notion of a one-time signature. So this is a hash-based signature scheme that can only sign a single message. And the reason is that the signing of the message involves revealing partially revealing your secret key. And if you over-reveal, if you sign two messages, then now you allow an attacker to forge signatures. So these are secret keys that are only meant to be used once. It's like a one-time bullet, if you will. And what Merkle did is that he took multiple one-time signatures and he basically placed them as leaves of a Merkle tree and Merkleized the whole thing. And the idea is that you go from a one-time signature scheme to a many-time signature scheme, right? Because now you can sign as many messages as you have one-time signatures in the leaves. Now, what we're intending to do with Lean Consensus is to have this massive Merkle tree with 2 to the 32 one-time signatures. So that's like 4 billion signatures, and that's enough to sign messages over something like 4 centuries. So when you register as a validator with your post-quantum pub key, that will be the Merkle root of an XMSS tree, which is humongous with these 2 to the 32 leaves. Now, the reason why we went with XMSS is that it is especially efficient, meaning that the amount of work that you have to do to verify your signature is extremely low. It's on the order of 200 hashes. So when you're snarkifying these signatures, you only have to mostly verify these 200 Poseidon hashes within your ZKVM, and this allows us using a single laptop CPU to aggregate 1,000 signatures per second, which is enough for our use case. And the big downside of Merkle signatures, or XMSS, which stands for Extended Merkle Signature Scheme, the main downside is that they're stateful, meaning that you need to remember how many messages you've signed, and you should never sign 2 messages with the same slot number, with the same count. Because if you do that, you kind of, shooting yourself in the foot. because now you're allowing an attacker to forge these signatures. But the good news for consensus is that you already don't want to be signing two messages at the same slot, because that's an equivocation and you would get slashed for that. So there's all sorts of infrastructure with the validators known as anti-slashing protection, which prevents a validator from accidentally signing two messages with the same slot. And so this downside is actually not a real downside in the context of proof of stake, but we still get all of the performance benefits. Now, one of the things that we want to do is also do aggregation of signatures at the execution layer. And the reason is that if everyone were to migrate away from ECDSA to these hash-based schemes, then we would have, roughly speaking, a 10x degradation in TPS. So Ethereum L1 would go from 25 transactions per second to 2.5 transactions per second, which is completely unacceptable. And so one of the ideas is to reuse the Lean VM infrastructure that we have at the consensus layer to aggregate these XMSS signatures, but to do that at the execution layer with stateless signatures. So these would be hash-based signatures that don't have this issue that I mentioned, which would be very dangerous for normal users to handle. And the primary scheme that has been standardized by NIST is called Sphinx Plus. So these are the hash-based signatures that are a few kilobytes in size.
And these are stateless.
Stateless, exactly.
That's the main advantage here.
This is the good thing. Yeah, you don't have to keep track of a slot number or nonce.
So going back to that Merkle signature, so each leaf in that Merkle signature is a private key. Is that what it is?
Yeah, exactly. So the way it works is that you sample a bunch of secrets, for example, of size 256 bits, and then you hash them, and then you Merkleize the hashes. So this is what's known as a Lamport signature, a one-time signature. There's a few optimization tricks. One which is the Winternitz tricks, which leads you to Winternitz signatures. But the basic idea is always the same. You have these secrets, which you can think as being bullets, and the main thing that you can do is reveal or not reveal the leaves. And you can think of that as kind of firing the bullet. And you don't want to be firing too many bullets, because these bullets that have been fired are basically used to craft signatures, and so you only want to sign a single time, hence the name one-time signature.
So now, as a validator, when I register, I get a public key associated one of the leaf.
So you're going to register the root of the XMSS tree. So you have 2 to the 32 leaves. You're going to Merkleize everything. And by the way, there's going to be what we call a key generation process. So it's going to take time to generate all of these signatures and to Merkleize everything. It might take on the order of like an hour or so. If you have a MacBook, for example, you might spend an hour or so generating all these keys, and that's going to be a one-time thing that you're going to have to do to register your validator. And your pub key is going to be the root of the tree, and every time you sign, you're going to do 2 things. You're going to reveal the bullets of the one-time signature, and you're going to have the Merkle path that basically connects the root of the one-time signature all the way to the XMSS root.
So every validator has its own tree. It has 4 billion leaves. That
Yes.
is, it has 4 billion one-time secret keys, and it should use, every time it signs, it should use a different signature that traces a separate Merkle path. That's what's happening.
Exactly. Yes.
Okay. Now I understand. And does that mean, okay, so I have the proof, so I can always test that whether that other validator is signing it properly or not. So I can always verify that with the Merkle proof or the Snark proof in this case.
So we would have like these multiple layers of aggregation. So the bottom layer would involve gossiping these XMSS signatures. They're on the order of 2 kilobytes, and and then we're going to aggregate them into SNARK proofs. The SNARK proofs are on the order of 200 kilobytes, so they're 100 times larger. But beneath them is going to be much more than 100 XMSS, and then eventually we aggregate the aggregates. So we take multiple 200 kilobyte proofs, and then we squish them into a final 200 kilobyte proof. And this one proof is going to have tens of thousands of signatures underneath it.
So moving over from the cryptographic part, so how do you see the role of rollups in this Lean Ethereum world? Is there going to be some kind of evolution in the view that traditionally has been ascribed to rollups, or is it going to be the status quo will remain the same?
Yeah, so I guess the two layers that are most relevant for rollups are the data layer and the execution layer. At the data layer, we already talked about this vision of the Teragas frontier, where all of the rollups combined would have 10 million transactions per second, which is 1,000 times more than the L1, which can only do 10,000 transactions per second. So kind of what I'm envisioning is that the vast majority of the throughput, 99.9% of it, from a transactional perspective, would go through the L2s and the rollups, and only 0.1% would go through the L1. But of course, these would be like the most economically dense transactions. Now, the other layer that's important is the execution layer, and I think the most salient innovation here is known as native rollups. So today, when you want to build a rollup, you have to build the state transition function that will validate the blocks, so that you can either use a fraud-proof game in the case of an optimistic rollup, or you can use a SNARK in the case of a ZK rollup. And there's two big issues with the maintenance of these state transition functions. The first one is that they're quite complex and they're probably buggy. And bugs are very bad because potentially it could mean that the entirety of the rollup could be drained in one fell swoop. The second big issue has to do with the maintenance of the EVM. So most of the rollups are trying to be EVM equivalent rollups, which means that when the L1 changes, the L1 EVM changes, the L2s also have to change in unison. And in order to do that, you need to have some sort of a governance process to evolve the rollup. But unfortunately, the governance process itself, the upgrade path, is itself a security vulnerability. And so wouldn't it be nice if you could have rollups that by construction are bug-free and they don't need to be upgraded whenever the L1 upgrade? And this is the basic idea of native rollups, where you can build a rollup where the execution state transition function is an exact copy of whatever is available at L1. So by construction, because it's an exact copy of the L1, it's definitionally correct. And whenever the L1 changes during a hard fork, all of the rollups would automatically change with it. And in order to deploy this precompile, this for the native rollups, it's quite convenient to first do the ZK EVM upgrade. And the reason is that when we have these ZK EVM proofs, well, you can just reuse the proof infrastructure for these native rollups, and you can essentially have unlimited scale. And so let me just briefly explain why the L1 will be limited. Well, one of the reasons why the L1 will be limited to 10,000 transactions per second. One of the reasons has to do with the fact that we're constraining ourselves in terms of the amount of proving resources for the L1. Specifically, we want the real-time proving to happen on less than 10 kilowatts. So there would be, for example, a cluster of GPUs that consumes less than 10 kilowatts, which is roughly 16 GPUs. And the reason we have this constraint is to have credible decentralization of the provers, so that we're not relying on data center proving. But the rollups, if they want to use data centers to do the proving, that's their decision. All we care about is that the proofs, the ZKVM proofs, are generated, and then they're just very cheaply verified on chain. And so effectively, what native rollups give us is an unbounded amount of L1 execution through these native rollups, and the only real bottleneck is the data availability layer. But again, the data availability layer should have a tremendous amount of throughput to support 10 million transactions per second.
Got it. So given that we have talked at the infrastructure level, I think I have the last question, which might be the most open-ended question: the economics. So you have now ZKVM for SNARKification at the consensus level. In future, you will have probably ZK EVM, which is doing there is a prover role. Then you have a different attester proposer, like you are removing which is modification on previous. You have fossil, where there is inclusion list. So there is a lot of moving vectors. So how do you, if I'm a user, how do you design the transaction pricing or opcode pricing around all these multi-dimensional moving parts? Is it in like a knapsack problem or something? So how do you, like, how are you guys thinking? Because this might be the most open-ended question, and it will probably evolve, I believe, as more and more things come up. But what is the current state of thinking?
Yeah, I think you put it quite well, in the sense that we have multiple actors. We have the proposer, the builder, the prover, the includer, the attester. And for each one of these roles, we want to have a credible story in terms of incentive alignment. And what we can do is basically go through all of the roles one by one and discuss what is the plan. So maybe the simplest is the includer role. And here, instead of relying on rationality, we're actually relying on altruism, meaning that we're expecting these actors to do this job for free. And the part of the reason that we believe that we can lean on altruism is because the job in and of itself is very cheap to do. What it really entails is listening to the mempool and picking the transactions in the mempool that are not being included in the chain, but really ought to be included. And when you're running a validator node, you're already listening to the mempool today. So it's not an additional load. And we are already relying on altruism for all sorts of tasks. So for example, if you're a node that wants to sync the history of the chain, for example, you will be downloading historical blocks from other nodes, and these other nodes are not getting paid for providing you this data. This is all done altruistically. And one way to get away with altruism is actually to lean on the client defaults. So if by default, when you run your node, you're an includer, then the majority of the network should be including, just because they won't bother putting the flag to disable including. Now, one thing that I should stress is that including might not be appropriate for some institutional validators that don't want to be touching, for example, OFAC transactions. And so, some subset, maybe 20%, 30%, some percentage will not be including, and that's fine. And inclusion works just fine, even if a small percentage of the validators has not opted out to including. Okay, now let's move on to the builders and the provers. So here the story is very similar to what we have today. Like all of the entities in the MEV pipeline are incentivized through fees and MEV. And this would be the exact same thing with proving. So when a block builder receives a transaction from the mempool, they want to make sure that the tip, meaning the fee that's associated with this transaction, is at least as large as the cost of proving it, because the cost of proving will be borne by the block builder. And the good news is that the proving costs are extremely minimal today. So a whole Ethereum block costs about 1 cent to prove, and let's say there's about 100 transactions per block. So we're talking about 1/100th of a cent of proving cost per transaction. So it's almost negligible and shouldn't affect the UX.
So on the proving cost, do you still need a multi GPU infrastructure for that, or that's you have a capital expenditure? You might not have an operating expenditure for proving. Is that a correct mental model here?
Yeah. So the 1 cent per block bakes in all of the cost. It bakes in both the operational expenditure, of the electricity, and the depreciation of the hardware, and it's basically benchmarked on the pricing that the cloud providers give you to rent hardware by the hour, for example. So it's a fully inclusive cost, and even though the builder has to pay for the proving, that doesn't necessarily mean that they are a prover themselves. So they can always outsource the proving to a specialized prover, and I guess that would be like BPS, builder-prover separation, very similar to what we have today with proposer-builder separation. And the nice thing with APS, attester proposer separation, is that the validators wouldn't be involved. There wouldn't be any proposer other than the block builder that won this specific slot. So that covers the includers, it covers the provers and the builders, and now there's this final very important role, which is the attesters. Now, the way that the attesters are incentivized is through issuance, and one of the great successes, if you will, of the Beacon chain is that we've been able to amass an enormous amount of economic security. So we have, roughly speaking, $100 billion of stake, and this is fantastic for economic security. But there reaches a point where more economic security is actually detrimental to the network because it has second-order consequences. So one second-order consequence is that we're overpaying for security. So we could be doing with a little bit less economic security and not have to pay for all of this. Another consequence is that if we have too much economic security, then most of the ETH, most of the pristine, raw, native ETH will be staking, and it won't be allocated to other use cases. So it won't be placed in Aave, or it won't be market making on Uniswap, or doing all sorts of other activities. And really, what this one way to phrase it is that it's unnecessarily lifting the cost of capital, and it's basically a drain on the whole Ethereum economy. And the third second order consequence is that because the cost of capital is so high, it incentivizes LSTs that basically allow you to get the best of both worlds. To be staking, but also be able to to participate in DeFi. But the big downside of LSTs is that the conversion from pristine ETH to an LST involves all sorts of risks. So if you look at Lido, for example, there's a governance risk, there's smart contract risk, there's slashing risk from the various operators that are staking, and it also affects the fungibility and the overall liquidity of the ETH markets, because now you have multiple assets that are fragmented, and so one of the worries is that if we have significantly more than, let's say, half of all ETH staked, we're potentially jeopardizing the moneyness of ETH. And so for the attester specifically, we have this proposal called attester stake capping, which would cap the total amount of ETH staked, for example, at 1/2 of all of the ETH. And the way that this would be done is by changing the issuance curve so that it goes to 0 as you get closer and closer to the
Really appreciate for going over the economics. I understand that it will change as newer circumstances or new developments come up. But yeah, so thanks, Justin, for going over the whole Lean Ethereum concept. It clarified a lot of my understanding, or maybe I'd say misunderstanding. So it answered a lot of my questions. So really appreciate it for going over it.
Absolutely. Thanks for having me.